Hello, everyone. Today I will introduce Generative Cooperative Flows, or COOP Flow for short, a generative learning framework that integrates the strengths of two powerful paradigms, energy-based models and flow-based models. COOP Flow combines the complementary abilities of the energy-based model and the flow-based model. Specifically, the energy-based model, or EBM, captures complex dependencies and provides a scoring function for sample quality. Meanwhile, the flow-based model, such as Real NVDAI or GLOW, offers an invertible mapping between data and latent spaces, allowing for exact likelihood estimation and efficient sampling. Together, these models cooperate to produce efficient and high-quality generative results. These two models are trained via cooperative learning, which iterates three steps. First, the initialization step. The flow model generates initial samples. Second, the refinement step. These samples are improved through short-run Langevin dynamics guided by the energy-based model. Finally, the cooperative update step. The energy-based model is trained by maximum likelihood on the observed and refined samples, while the flow model learns directly from those refined examples. Why is the underlying motivation to train these two models together? Normalizing flows excel at computing tractable densities, but often fail to model complex structures realistically. Energy-based models, on the other hand, are highly flexible and expressive, but require expensive MCMC sampling. By training them together, the flow model learns to initialize the energy-based model's Langevin sampling process, effectively reducing the sampling cost and improving sample quality. Here's a quick reminder of what normalizing flows do. They learn an invertible transformation between data and latent variables, allowing exact likelihood computation for maximum likelihood estimation. Such models also serve as efficient generators. They first sample latent variables from a Gaussian distribution and then map them back into the data space through an invertible transformation network. Let's introduce some notations. Let X denote the data, for example, an image, and Z denote the latent variables drawn from a Gaussian distribution Q0. To ensure exact likelihood computation, the transformation network parameterized by G alpha needs to be a sequence of invertible transformations, each with a Jacobian whose log determinant can be computed explicitly. Also, another key idea of the flow-based model is to choose each transformation so that its Jacobian is a triangular. This makes the computation of determinant simply the product of its diagonal elements, which allows for efficient computation during training and inference. The training of the flow-based model can be achieved by maximum likelihood estimation. However, despite this mathematical elegance, the strict design constraints of flow-based models limit their expressiveness. As a result, when trained alone, flow-based models often produce overly smooth or unrealistic samples, which motivates the need for cooperative refinement. Now let's introduce the Langevin flow. The Langevin flow comes from the theory of energy-based models. Let me briefly introduce the energy-based model. The energy-based model defines an unnormalized probability distribution with the energy function parameterized by neural network. The trainable parameters inside the neural network can be optimized by gradient-based maximum likelihood estimation. The maximum likelihood learning gradient can be approximated by Langevin sampling. The Langevin sampling technique is an iterative, gradient-based algorithm that progressively refines an initial noise sample, typically drawn from a uniform or Gaussian distribution. In theory, as the number of iterations approaches infinity and the step size approaches zero, the refined sample converges to an exact sample from the probability distribution specified by the energy-based model. In practice, we use a fixed number of Langevin steps to implement this dynamics. The resulting distribution, defined by this short-run Langevin process, is well-defined and can be implicitly represented. We refer to this as the Langevin flow. This iterative refinement process is powerful, but computationally expensive. That's why cooperative initialization from a flow model makes such a big difference. Now we bring the two types of flows together, the Langevin flow and the normalizing flow, and introduce the co-op flow algorithm, which trains both models jointly. The algorithm proceeds iteratively as follows. At each iteration, the normalizing flow first generates initial samples by transforming latent variables drawn from a Gaussian distribution. Next, the Langevin flow refines these samples through gradient-based updates. Both models then learn from the refined examples. The Langevin flow improves its energy function, and the normalizing flow learns to produce better initializations. After training, the resulting generative model is called the COOP flow, which is a normalizing flow followed by a Langevin flow. COOP flow aims to transform the prior Gaussian distribution Q0 into the target data distribution by the normalizing flow and the Langevin flow together. The Coop flow model can be viewed as a latent variable generative model, where the latent variables Z follow Gaussian distribution Q0. The overall transformation consists of two components, G alpha and F theta. Here, G alpha is the mapping of the normalizing flow, which transforms Z theta into an intermediate sample X hat, and F theta denotes the mapping realized by a T-step Langevin flow, which further transforms X hat into the final data sample. This model can also be used for data reconstruction. Given an observed data point X, we can infer its corresponding latent variable Z. Specifically, we first estimate the intermediate X hat that can best reconstruct X by minimizing the reconstruction loss via gradient descent. Then, using the inverse transformation of the normalizing flow, we compute the associated latent code Z. Let's look at how Coop flow can be applied in practice. It serves as a general-purpose latent variable generative model. Some main applications include, first, image generation, producing realistic samples from scratch. Secondly, pattern completion, image inpainting. Thirdly, image morphing, interpolation in latent space to achieve smooth transitions between images. Here are examples of images generated by Coop flow on 3 datasets. All images are 32 by 32 pixels. You can see that Coop flow captures fine-grained details and natural diversity across domains. We further show that Coop flow is also capable of doing image inpainting. Similar to image reconstruction I mentioned above, given a masked observation along with a binary matrix indicating the positions of the unmasked pixels, we optimize X hat to minimize the reconstruction error in the unmasked area. In this figure, each row shows one example of inpainting with a different initialization of X hat provided by the normalizing flow. The first 20 columns display the inpainting results at different optimization iterations. The last 2 columns show the masked images and the original images respectively. We can see that the model can reconstruct the unmasked areas faithfully and simultaneously fill in the blank areas of the input images. With different initializations, the model can inpaint diversified and meaningful patterns. Here we show image interpolation in the latent space. The leftmost and rightmost images are observed samples, while the intermediate columns represent interpolation results. As you can see, the transitions are smooth and coherent. Co-op flow captures continuous latent representations that reflect meaningful image variations. To conclude, co-op flow integrates the strengths of Langevin flow and normalizing flow in an energy-based generative framework. It achieves both efficiency and high quality in sample generation. It can be used for image generation, pattern completion, and image morphing tasks. Overall, it bridges the gap between flow-based models and energy-based learning. Thank you for listening.